Okay guys, today we start the material for test 4. And we're going to start today with rigid bodies. Up to this point in time, we have been dealing with the particle model, which treats any object as if it's a point mass, which means that when you apply a force to that object, it will only cause translational motion, because all of the forces are presumed to go through the center of mass of the object. Okay? Today we move on to rigid body, where we start to take into account the shape and mass distribution of the object and whether the object is constrained or unconstrained. Right? So, what is a rigid body? A rigid body is an extended object, an object that has size and shape with a mass distribution, and it does not change its size or shape when it moves. 3 types of motion we can talk about with rigid body: translational motion, motion of an object as a whole along from one location to another following a trajectory. Okay, what we talked about with the point model. Rotational motion, motion where the object rotates about a fixed point. Every point on the object then is undergoing circular motion. And combinational motion, where the object rotates as it follows the trajectory. So you can see in these 3 diagrams, translational motion, pure rotational motion, and combinational motion. All right, now, let's remind ourselves about circular motion and link it to rotational motion. Now, when an object undergoes rotational motion, each point on the object is rotating and is following a circular pathway about a pivot point. Okay? A pivot point is a point about which the object is rotating. A pivot point could be because of a constraint like a nail or an axle or a hinge, or it could be unconstrained, and the pivot point for an unconstrained object is the center of mass. Okay? So, when we look at rotational motion, we're looking really at circular motion. Last time we talked about circular motion, we talked about both tangential velocity and angular velocity. Since we're describing an object that as a whole is undergoing rotational motion and every point on that object is undergoing circular motion, using tangential velocity to describe the motion is definitely inconvenient, because each point moving out from the pivot point to the edge is going to have a different tangential velocity. To describe the object as a whole, we're going to want to use angular velocity, and if it's changing angular speed, angular acceleration, because both of those will describe the motion of the object as a whole. So again, all points on a rotating object have the same angular velocity, but each point has a different tangential velocity. Remember that angular velocity is change in angular position with time, and the relationship between angular velocity and tangential velocity is tangential velocity equals omega times r, the radius. Okay, also remember that angular acceleration equals change in angular velocity with time, and the tangential acceleration equals alpha times r. Also remember that a sub r, the radial acceleration, is equal to v sub t squared over r, or omega squared times r. So every point on the object is going to have a different radial acceleration because it's going to be at a different location from the pivot point. So if there's a change in angular velocity, there's a change in tangential velocity for every point on the object. that table 12.1 here just reminds you the relationship between angular velocity, final and initial when we have an acceleration. Those are identical to the equations that we saw for linear motion. All right, now I've hinted at this earlier that we have for objects moving along a circular pathway, we have a counterclockwise direction and we have a clockwise direction. We know if the angular velocity and angular acceleration are counterclockwise, we call it positive, and if it's clockwise, we call it negative. Okay? Now, if the angular velocity and the angular acceleration both point in the same direction, then we have an increase in speed. They point in opposite directions, we have a decrease in speed. If you look at the pretty pictures here on the screen, you know, it's just reinforcing that. Now, let's do just a simple problem 2 here at the end of the chapter, just to kind of get back into the circular motion wheelhouse. Okay, so let me get problem 2. All right. Okay. It says the skater holds her arms outstretched and she's spinning at 180 RPMs. So 180 RPMs. That's our angular speed, 180 revolutions per minute. It's not in SI units, but we've got it. And it says that her hands are 140 centimeters apart. Okay, so that's the diameter, 140 centimeters. That means the radius is 70 centimeters, 0.700 meters. And we're asked to find the speed of her hands. So we're asked V sub t. All right, guys, let's look at the board. Now, first thing I need to do is I need to get the angular velocity into correct SI units. So there's 2 pi radians for every 1 revolution, and for every 1 minute there is 60 seconds. So 180 times 2 times pi divided by 60 gives me 18.8 radians per second. V sub t equals omega times r, so it's 18.8 radians per second times 0.700 meters. 18.8 times 0.700 gives me 13.2 meters per second. Okay, now that's just a kind of consider that a warm-up problem. All right, moving on. Let's talk about center of mass. The center of mass is a point about which an unconstrained object with no net force along the x and y axis acting on it will rotate. Okay? The center of mass remains motionless while all other points about it move or rotate. For a 2D object, there's an x position of the center of mass and there's a y position of the center of mass. We could also define the center of mass as the mass-weighted center of the object. Okay? Now, so it says, you know, if this object rotates about this point, that's its center of mass. And it's going to have an x position and it's going to have a y position. To locate the center of mass of an object requires we do a calculation based on the mass-weighted position of the center of the object. So we think about breaking the object up into little mass pieces, okay? We take the mass of each little piece times its x location and add them together and divide it by the total mass of the object. Take the mass of our little pieces multiplied by their y position and divided by the total mass of the object. Now, we're going to look at a basic problem. We're going to look at problem 7, the end of the chapter. So if we look here at problem 7, it says the three masses shown are connected by massless rods. What are the coordinates of the center of mass? Okay, well, our first little piece here, piece A, is a 200-gram piece and it's at location 0. And part B is a 300-gram piece at 12 centimeters, and C is a 100-gram piece at 12 centimeters. Okay, so x of the center of mass is going to equal 200 grams times 0 plus 300 grams times 12 centimeters plus 100 grams times 12 centimeters, and divide it by the total volume, the total mass, which is 600 grams. So if we do that, where'd my calculator go? There it is. So I have 200 times 0, which is 0, 300 times 12, plus 100 times 12, divided by 600, and the x position of the center of mass is 8 centimeters. Now for the y position of the center of mass, I have 200 grams times 0 plus 300 grams times 10 centimeters plus 100 grams times 0 divided by 600 grams. So 300 times 10 divided by 600. I get 5 centimeters. Not bad, right? You can do a problem like that. For solid objects, okay, not little blobs connected by massless rods, we'd have to use integration to find the center of mass. So x of the center of mass is 1 over the total mass, the integral of x dm, and y of the center mass is 1 over m the integral of y dm. Now, before you panic, if an object is regularly shaped geometric object and it has a even mass distribution, the geometric center of the object is also the center of mass of the object. Okay? If an object is rotating, then the parts of the object are moving, and therefore it's got to have kinetic energy. More specifically, rotational kinetic energy. Remember that kinetic energy is 1/2 mv squared, and we would calculate the kinetic energy for every individual point on the object. But you know, we have already talked about the fact that that's very inconvenient. So let's think about the fact that V sub t is equal R times omega. And the total kinetic energy then can be sum of the kinetic energy of all the parts. So rotational kinetic energy is 1/2 the sum of the masses of the little pieces times the R location of all the pieces squared times omega squared. This part in parentheses, we're going to pull out, and we're going to give it its own symbol. Namely, it's going to get the symbol of a capital I, and it's called the moment of inertia. Okay? The moment of inertia is a measure of how hard it is to change something's rotational motion. Now, on page 347 in your textbook, there are equations for the moment of inertia for common shapes and common placements of pivot points. I don't expect you to memorize this, but I do expect you to be able to use it. So if I give you an object, okay, it's going to relate to one of these, and you should be able to calculate its moment of inertia. So since the pivot point is a point about which the object is rotating, it could be an axle or a pin or the center of mass if it's unconstrained. So we have kinetic energy of rotation is 1/2 I omega squared, if you know where the pivot point is. If the pivot point you're given is not lining up with one of the pivot points on the table up above, there is something called the parallel axiom theory. Okay? It says I is equal to the moment of inertia of the center of mass times the mass of the object times the distance squared to the pivot point from the center of mass. Now, what do you think causes an object to rotate? If we think about motion that we've already talked about, we know that to make an object move requires us to apply a force. So if an object is initially sitting still, we've got to apply a force to make it start to move. If we want to speed it up, we've got to apply a force. If we want to slow it down, we've got to apply a force. And therefore, if we want to make something rotate, we're going to have to apply a force. Okay? What we want to talk about now is what kind of forces make things rotate. Now that I have an object that is a rigid body that has a shape to it, we want to think about whether the force is passing through the pivot point or whether the force is not passing through the pivot point. Now, why is this important? A force passing through the pivot point does not cause rotation. For an unconstrained object, a force passing through the pivot point or the center of mass, if the center of mass is a pivot point, will cause translational motion. But any force passing through the pivot point will not cause rotation. Forces further away from the pivot point cause a greater angular acceleration than those closer in. A force perpendicular to the line connecting the pivot point and the point of force application has a greater effect than those at an angle other than 90 degrees. Now guys, you can try this yourself with a door. Okay, let's go over here and look at the door. Okay. All right, now, the hinge is the pivot point. If I push like this, door doesn't go anywhere. Okay? If I push here, I cause a rotation. Now, if I move further toward the hinge and I push with the same force, notice I don't get the same angular speed. And if I were to push with an angle instead of head on, notice it doesn't rotate as fast. So where you apply the force relative to the pivot point, what direction you apply the force relative to the pivot point, all affect how the object is going to respond in terms of rotational motion. Now I'm going to draw a picture. PP stands for pivot point. Okay, so if I apply a force F1 here, that pivot point is going to apply a force that opposes that force. Nothing's going to happen. Now, if I apply too hard, of course, I can break the axle or I can break the pin that's restraining it, but that's different. Now, let's apply another force. Let's apply a force F2 right here. Okay? And then let's apply a force F3 right here. And then one more for good measure. I'll apply force F4 right here. Now, if all four of these forces are the same magnitude, we've already established that force 1 isn't going to do anything when it comes to rotational motion because it's pointed at the pivot point. If I look at force 2 applied at this pivot point, it's going to want to try to rotate it clockwise. This one's going to rotate it counterclockwise. Okay? And this one, when it's at an angle, okay, I want you to think about the fact that it's going to have an F4 radial and an F4 tangential. Only the tangential component of that force is going to work toward rotating it. The radial component of the force is along the connector line with the pivot point. Okay, it's directed along the pivot point, and any force passing through the pivot point is not going to cause a rotation. So guys, this brings us back to thinking about our RTZ axis. Okay, so let me draw here. Let's put a pivot point here. Our point of action here, and I'll draw a force here, F. Okay, this would be our T-axis. This is our R-axis. Okay, so I break that force up into components. This is force tangential. This is force radial. only this component of the force is going to cause a rotation. Now, if we look at this angle is called phi. The magnitude of the force tangential is going to be the magnitude of the force times the sine of the angle phi. Because remember, we could also think about that as f sub t, and it's opposite the angle, so we're going to use the sine of phi. Okay? Only this portion of the force is going to cause rotation. Now, if we combine the magnitude of that force tangential with its location from the pivot point, we get something called torque. Okay? T-O-R-Q-U-E. Its the symbol is a capital tau. And torque, the magnitude of a torque is equal to the magnitude of F sub t times r, the distance from the pivot point. If it causes a counterclockwise rotation, torque is going to be positive. If it causes a clockwise rotation, torque is going to be negative. Now, I'm used to calculating it this way and then saying that, torque would be positive for counterclockwise, torque would be negative for clockwise, reinforcing the idea that we have something that has a directionality to it. Another way that you can do this, okay, there's my pivot point, and let's say this was my force F here. There's the location. Okay? Now, if you think about this as our vector R, pointing from the pivot point to the location of action, remember that I could move it on out, and I'm not quite to scale here, but we could think about R, starting at the same pivot point. If you go counterclockwise from R, the extension of the radial line, back to the force, and we call this the angle phi, then torque is equal to the magnitude of the force times the sine of phi. Okay? Because notice this is going to be an angle greater than 270. Right? But this is another way that you can calculate torque, and this one gives you the angle directly. If you use this angle, okay, I'll call this one beta. If you were to use beta, which is what I learned to use when I sat where you do, you have to assign clockwise, counterclockwise yourself. Okay? But you can do it either way. Now, if there's only one force acting on the object, then calculating the torque on the object is easy. If you got multiple forces acting on an object, then we would probably need to do the sum of the torques. Torque net is equal to the sum of the torques. If the net torque on an object is 0, then there will be no change in rotational motion. If the net torque is not 0 and constant, then we can expect a rotational acceleration that is constant. Okay? All right, now what this is leading to is the fact that the sum of the torques, bring you back over here with me for a second. The sum of the torques acting on an object is equal to torque net, which is equal to I alpha. Okay, write that down, we'll come back to it. All right, kind of foreshadowing here. Okay? Now, when we look at an object and we think about an object's rotation, if I were to hold this box out like this, okay, and I'm just gripping it with my fingers, let's say here, the box wants to rotate on me. And that's because there's force due to gravity acting on the box, and the force due to gravity on every point on this box is pulling down. I'm pinching here. That force is perpendicular, okay, to my pivot point, and it wants to rotate it. So when I have an object suspended, then the weight of that object, or the force due to gravity acting on that object, wants to cause the object to rotate. We always assume that the total weight, i.e. the total force due to gravity acting on the object, is acting at its center of mass. So the torque due to gravity is mg times the position from the pivot point times the sine of whatever angle phi. So if I had this up like this, okay, radial position there, force due to gravity here, okay, we'd have that angle. All right, now, I hope that you're getting to the point where you're starting to get some aha moments. For translational motion, remember that sum of the forces equals mass times acceleration, okay? So that when I have forces going through the center of mass, they cause a translational motion. And if you have a net force that's not zero, you get an acceleration, either along the x-axis or the y-axis or the x and the y-axis. For rotational forces, sum of the torques equals I alpha. So that when you have a net torque acting on an object, you have an angular acceleration. Okay? So we're going to do one, maybe two problems here where we're looking at sum of torques. So let's start off by looking at a really simple problem. We're going to look at problem 18. Here on page 330. It says, what is the net torque about this axle? Okay, so I'm going to redraw this picture. I've got a 30 newtons force up top, and I have a 20 newton force below, and the diameter of this guy is 4 centimeters, so the radius is 2 centimeters. Okay, so I've redone my picture. Now, this is a 90-degree angle. Okay? If I get my torque top, I'm going to go ahead and calculate, well, let's see. I'm I'm going to do it the way your book does it, although it's a little awkward for me. The torque from the top is going to equal the magnitude of the force, 30 newtons, times the magnitude of R, 2.00 times 10 to the minus 2 meters. And if you think about this as R and extending R this way and going counterclockwise, I'm going to take the sine of 270 degrees. Okay? So 30 times 2 exp 2 negative times 270 sine, and I get a minus 0.600, and the units are Newton meters. And torque is a vector. If I look at the torque from the bottom, it's going to be 20 newtons times 2 times 10 to the minus 2 meters. Now, I extend this out. This is R. Counterclockwise around to the force. That's 90 degrees. The sine of 90 is 1. So 1 times 2 exp 2 negative times 20. That gives me a plus 0.400 Newton meters. So the sum of the torques here would be a minus 0.600 Newton meters plus a plus 0.400 Newton meters, which gives me a net torque of minus 0.200 Newton meters. Not bad, right? You should be able to do sums of torques. Now, I also have 20, 21, and 23 listed there. If you're watching a video, I do not want to drive you absolutely crazy here. So I think probably just doing something, well, let's, yeah, let's move on to other things. Okay? Because it's just repeating the same thing over and over again. That's pretty simple. Now that we're dealing with rigid bodies, some old assumptions that we were making we're no longer going to make. Namely, we are no longer going to assume that a pulley is massless and frictionless. We now have to deal with the fact that the pulley is a rigid body that is undergoing rotation as the rope that's going over the pulley moves. Okay? The tangential velocity of the pulley is going to be the same as the velocity of the rope. And if the rope is accelerating, then the acceleration of the rope equals the tangential acceleration of the pulley, which equals the radius of the pulley times the angular acceleration. Okay? Also, since there is a rotation of the pulley, that means that there essentially has to be a net torque on the pulley, which means that the tension in the rope on the two sides of the pulley can no longer be assumed to be the same. So let's look at a problem of my invention. It says two masses, one a 1 kilogram mass and the other a 3 kilogram mass, are hanging over a pulley of mass 0.5 kilograms in diameter, 0.25 meters. Okay? Find the acceleration. let's find the acceleration of the, and I evidently can't type today, one kilogram mass. Okay, so let's draw a picture. Pictures are very important in the world of physics. They help us visualize what we're doing. So I've got a pulley here, and I have a rope going over the pulley, 3 kilograms over here, 1 kilogram here, and this is a 0.50 kilogram, and it's got a radius of 0.25. Now guys, this is a 3-object system now. I've got the 2 hanging masses in the pulley. For the hanging masses, I want to do free body diagrams. Okay, it's got a force 1 here, and it's got a force due to gravity 1 here, and I expect acceleration to be upward, A1. Our 3 kilogram mass, I'm going to have it having a force F2 here, T2 there, let's make this a T1. Force due to gravity 2, and I expect its acceleration A2 to be down. Now let's think about the pulley. That's going to have a force, a tension T3 here, and a tension T4 here. Okay, I'm expecting this guy to have an angular acceleration in this direction. Now let's figure out our forces due to gravity. So FG1 is going to be 9.80 newtons. FG2 is going to be 3 times 9.8, 29.4 newtons. And those are magnitudes. Okay, now let's think about our acceleration, our constraints. 1, I know that T1 is going to equal T3 because that's a continuous rope here. I'm going to call its magnitude T1. Over here, I know that the magnitude of T2 is going to equal the magnitude of T4. I'm just going to call that T2. Okay? I know that the magnitude of A1 has to equal the magnitude of A2. I'm going to call that A. And I know that the magnitude of alpha is going to equal A over R. Okay? So, let's start building equations. All right, for my 1 kilogram mass, I have T1 plus force due to gravity 1 has to equal 1 kilogram times A1. So I have T1 minus 9.80 newtons has to equal 1 kilogram times A. For my other hanging mass, okay, this is the 1 kilogram mass. For my 3 kilogram mass, I've got T2 plus force due to gravity 2 is 3 kilograms A2. So I have T2 minus 29.4 newtons equals a minus 3 kilograms A. For the pulley, okay, I'm going to look at the sum of the torques. I'm going to have T3, the magnitude of T3, times R, 0.250 meters, having to C. And that's going to cause a positive torque. From a 3 kilogram, I'm going to need it to get a negative torque, so I'm going to have minus 3 kilograms times 0.250 meters has to equal I alpha.